magic in the world happened, but there was something that came in when he come in to work with me that there was something different. And then, so Max has been working in my lab. We're on the save the world kind of physics, and it was a really hard problem. And then he took it and ran with it, and he has been living in the lab essentially, and given it his all. And when people come to my lab, you'll see Max working so hard, intensely on this problem. And so it's a great pleasure to introduce Max.
Thank you. Hi everyone. So, quick show of hands. How many of you live in California? Everyone, awesome.
Good one.
You all got that one right. So you may have noticed the past few years we've been running short on rainfall. This is a map here that shows the precipitation globally. And California is right here in the lowest category globally. So, and this is average annual precipitation in millimeters? I think it's millimeters. So we have very low rainfall, so it's a problem for us here, also in North Africa, Ethiopia, and in Central Australia. Those are pretty popular deserts. So according to a study done by U.S. Geological Surveys, about 0.4% of the Earth's fresh water is suspended in air. And that equates to 12,900 cubic kilometers, which equates to only about 2.5 centimeters of rainfall globally if it were all to just come down. But it's still a significant source of water that it's still a significant source of water that we can tap into using the technology of condensation, which is what I've been working on a lot. Currently there are many companies utilizing condensation methods to bring potable water to people worldwide. First, I'll introduce them to you. Then I'll go through some math that I've done for preliminary calculations to obtain my objective numbers for this project. Many designs were built and tested here in the lab, Sonoma State, by me. And they all offer some kind of insight into what is really happening in collecting water from the air. These designs that I've made are limited for being low cost and hand built. This tower was supposed to make hundreds of gallons each night, but it only produced 5. This is Nappin's air well, and this is his diagram over here. And he tested it in the lab using a smaller scale, and his data just didn't scale up to this 600-foot tower that you can still visit today in France. Like I said, this design is passive, meaning that it only relies on solar radiation and day and night cooling. There's very little upkeep, and there's little to no, there are no moving parts. The research and experiments done by Dr. Gurja Sharan in India about dew harvesting was a great basis for my project. Dr. Qualls gave me a book, and it was a really great read. And, he has some very interesting results. Dr. Sharan collected dew using passive condensers, which are 1 square meter, and he used different materials, including aluminum, galvanized iron, and plastic. These are materials that are used, they're very popular for roofing in India. After observing year-round dew harvest, he noticed that the optimal dew season is October to May, it's 8 months. This may be different for California, however. By measuring the surface temperature overnight, plastic was found to be the best material for collecting dew. His data concludes that he also tested cardinal direction. His data concludes that the north-facing condensers collected the most dew, which was over 16 liters, and that was over an 8-month period. And I believe his arrays were 5, so he had 5 cubic meters. And then, naturally, he wanted to expand his designs to a 9 by 9 meter condenser, but it did not perform as well as the smaller condensers, similar to the napkin situation. So these guys, the next 2 companies that I'm going to talk about, create atmospheric water generators. They're different from harvesters because the generators require an alternative energy source to drive the condensation process faster. What's really cool about these generators is that they produce thousands of liters a day. And this company, Eagle Water, is based in France. With these, you just can't get these results with passive condensers. And these guys are really cool for using wind and solar to drive that and reduce their carbon footprint. And then another company here, Ecoloblue, makes atmospheric water generators. They make home and office designs, as well as these trailers that are used for military and construction corps that may be isolated from water supplies. So there's definitely a commercial demand for this technology, for any kind of technology that can tap into atmospheric water. And now it's time to talk about my atmospheric water harvesting methods. First, I'll go over some preliminary calculations. The problem here is how much water can I make using 1 kilogram of ice? To do this, use the principles of thermodynamics, and so we have 1 kilogram of water. The latent heat of melting of water is 334 kilojoules per kilogram. So 1 kilogram of ice times this number here gives you how much energy of heat is absorbed by the system. 334 kilojoules of heat absorbed by ice melting. And then I use the latent heat of evaporation, which is much higher. And then I divided the energy that we have by this number to get this number, this mass of water right here. Since the density of water is a kilogram per liter, I found that 147 milliliters, that box is supposed to be up there. 147 milliliters is the yield of a system with 100% efficiency. So that's the goal number. Speaking of efficiency, this is a simple equation that I use to calculate the efficiency of each design based off of the amount of dew that was actually collected off of the system. So some systems were 1 kilogram of ice, others were more, so that affects the efficiency. As it says here, efficiency depends on how much mass of ice I used, also the relative humidity. So this psychrometry is a study of moist and humid air, and this chart is the great scientific contribution to my project. Here we have different rating relative humidity, and this is the dew point. So at this temperature, this is the temperature that the system has to be below in order to create water and draw it out of the air. And as you can see, with the higher relative humidity, dew point is always higher. So the temperatures at which the system gains water is all below the line. In a room such as this one, we have 40% relative humidity. So we follow this line to find the dew point using the air temperature here, and that's the temperature we have to achieve to create dew. I also found that the efficiency of the system changed with the different mass of ice. So here we have different masses of ice, and each time the mass doubles. However, we saw that the condensation kept jumping more than double. And these systems were all tested simultaneously so they all have the same conditions. And this is the efficiency calculated with the simple equation I used earlier. And here's a graph of those points, and here's a fit, series fit done by Excel. This is showing deviation from a linear behavior. Next, I tested material properties. Thermal conductivity is how well heat transfers through the material. Metals have high thermal conductivity, so the material will facilitate heat transfer at a faster rate. On the other hand, plastic has a very low thermal conductivity. This makes the material good for keeping the system cold. Emissivity is how well the material emits thermal energy. Values range from 0 to 1. Metals have very low emissivity, and like aluminum and copper, whereas plastic has very high emissivity. So again, this is a optimal material, also found by Sharon. Sharon also found that plastic was better for his passive condensers. And then heat capacity is the amount of energy needed to change a material by 1 degree Kelvin. That's not so important though. It was just on there. So here's my first setup. Bag of ice is melted. The reservoir is a plastic cup. Here are the conditions. Relative humidity is about 40%. Air temperature is room temperature. I used a Pascal high sensitivity force sensor to measure the force that's created by this system, and everything is being recorded. I divide the force that's read to the computer by the acceleration due to gravity to get the mass of the water. This is the condensation rates of different systems. The green is 1 kilogram of ice, and then the next 2 trials I added salt to see if it had any effect, which it definitely did. But it wasn't able to produce as much here per kilogram, so the efficiency dropped with salt. And I believe that that's because when you add salt to water, the system becomes more thermally conductive. So, as you can also see, the peak stops sooner than regular water. And that goes to prove that indeed the system is more thermally conductive and that it reaches equilibrium with the environment, which is this, faster. There's also this downward behavior that we can look at. That's evaporation off of the system. And this plateau behavior over here, that's what we want. That means that the reservoir that I used successfully prevented evaporation. However, there was some loss due to the design. With a plastic bag, you don't get a lot of control. So it's hard to replicate that amount of evaporation per trial. So here's some quick words. I've concluded that salt should not be added to the system. The efficiency with just ice was 20%, and then the efficiency was 10% here. More percent of water evaporated. And also I noticed that when the salt was added, ice formed on the bag, and that probably inhibited dew dripping. This is the next system I set up. This was Dr. Qualls' original idea, and I've done what I can to improve it. It's called a double system because there's 2 systems of ice. There's this top one here, and this bottom one in here in this wind shell. This protects this system from wind, and also isolates the air that drops into and around that system, so that it has more time to It has more time to condense water. Over here. Here's my experimental data. This is big negative behavior, evaporation, bad. That's compared to the 1 bag of ice. We can see that it made more. However, we're using 2 kilograms of ice in that system. So the efficiency is actually half of what it looks like on the graph. The double system. Dew yield measured by volume was only 10 milliliters. The highest dew mass was 31 milliliters. The efficiency of this design is 10.5%. So when I tried to scale up because efficiency improves with mass, I had to stop using the force sensor and use a big old 4 kilogram air guide, 2 kilograms of ice in here, and the dew is collected independently. Here's the results from all my double experiment. At this point here, the yields go down a lot. And this was because there's a fish tank in the lab, and when we turned it off, all of my yields were going down. And it was so stressful trying to figure out why, and I just could not replicate any results. But I figured out that it was relative humidity caused by the fish tank in the lab. This is my prototype. It's called a portable well. Condensation occurs inside these plastic tubes that go through the bottom. Ideally, there should be a lot of tubes. It should be almost full, so that you won't need as much ice to fill it up. And the efficiency of that yield was a sad 5 milliliters. But it was tested outside on a day when relative humidity was 90%. So a lot of work can still be done on that. In conclusion, a system that could yield 147 milliliters of water from 1 kilogram of ice is 100% efficient. If 40% can be achieved, then this technology becomes commercially feasible. Plastic has the low thermal conductivity and high emissivity, making it optimal material for these designs. Increasing the mass of ice in the system also increases the efficiency by a small amount. And the dew point of air depends on the temperature and the relative humidity. The higher the dew point, the more time granted for systems for condensation. An ideal system would be a thin, rigid plastic that could hold a large mass of ice over 5 kilograms. The bags couldn't hold any more than 4 kilograms in the lab. It was really hard to get that going. Finally, I'd like to say thank you to my mom, my grandparents who came all the way from SoCal. Good job, guys. Dr. Qualls, it's been a very pleasant experience. I felt like I had a second home in the lab, honestly. Thank you. Yeah. Thank you, Dr. Gurja Sharan, for his excellent publications on dew collection, and thank you to all my teachers, Dr. Jones, Dr. Shee, Dr. Severson, Dr. Qualls, all you guys. And you too, Dr. Target.